Just very much in the spirit of the previous talk, I will talk about the quantum simulations that we are performing in our group. And we are particularly interested in characterizing many-body systems through their entanglement. So if we just think of a generic many-body system, we can maybe see some kind of order in these systems. So this would be just particles that would be arranged on a checkerboard lattice. So in this case, it's very clear we have a very clear order parameter of the system, which just quantifies how many particles are sitting on the even and the odd sides of this checkerboard pattern. Now, if each time I would look at this quantum many-body state, if each time I would see exactly the same pattern here, I know this is an unentangled state. So what I have here is each time the very same snapshot. Now, let's assume that each time I would look at this snapshot, I would see something else. For example, once I would see atoms, a slight modification of this checkerboard pattern, and another time that I would look at these patterns, I would have another modification. So some of the particles, they go around there. Essentially, the state fluctuates around its ordered state locally. But on a global scale, the pattern is still intact. We always see the checkerboard pattern in these systems. So here we have a locally entangled state. What I want to talk today about is more complicated entangled systems. So what I'm thinking about are states where, if I look at it at a single snapshot of this quantum state, I would not be able to identify any order whatsoever. So these particles here, they're just distributed at a seemingly random pattern. Another time I would look at this, maybe the atoms sit elsewhere, and it looks again very random. Now, what I would have now to do is to look at this state many different times, potentially even of different bases, but maybe in a single basis is enough to look at it a lot of times. And then if I combine my knowledge of all those different snapshots, I might be able to find new patterns in these systems where actually some structure is in the entanglement hidden. So I need very complex observables here. I need a lot of different snapshots of the same quantum many-body system to understand what kind of structure is hidden in that state. These are the kind of systems that we are interested in, complex entangled states that appear at first sight unordered. And I will today talk about very different systems that we try to characterize with different methods to capture these kind of entanglement in the system. So the goal is really, given you have some many-body state, what are the right observables to characterize the entanglement that is in the system? So really targeted for the exact state that I'm interested in. So in order to do so, we need very high fidelity and very precise techniques to actually manipulate and probe our quantum state. And the way we do that is with single atom control in an optical lattice. So what we do is we first cool ultracode, we cool rubidium atoms, load them in an optical lattice. These are bosons in this case, and then these atoms, they can collide on the same lattice side, and they can tunnel between neighboring sides. So we have a very precise realization here of the Bose-Hubbard model that we've been mentioning, that was mentioned already a few times. Now you see here actually a cartoon of our vacuum chamber. So down here, this is inside the vacuum chamber, and this line separates vacuum from air. And what we do now is we project laser beams through this objective, and over here you can see the atoms that are trapped. So they're actually these atoms are now subject to diverse laser beams that manipulate and probe those atoms. So these beams here, they would create this optical lattice in which these atoms are living. Now, on top of that, we can also look at the atoms by looking at fluorescence images of these atoms. So there's a light that is scattered through this microscope objective on a CCD camera. And then what we can do is we can take a picture of these atoms in this optical lattice, a snapshot of the quantum state, and we get these kind of pictures. So you see here hundreds, up to 1,000 atoms in this optical lattice. And if you actually zoom in, you see that there is really an underlying lattice structure. And on each individual lattice side, we see, is there an atom or is there no atom? And we can do this with a very high fidelity, far beyond 99%, telling if there is an atom on this particular lattice side or not. So it's really a collapse of this global wave function at a particular point in time where we probe it. Now, on top of that, we can also, so we use these pictures then, and then we binarize the fluorescence counts on each individual lattice side, and from that we get these kind of matrices, which are just fillings of ones and zeros, whether there was an atom or none. On top of that, we can also project light field light potentials that go beyond the single optical lattice by arbitrary potentials that we project through a digital micromirror device. It's beam shaping, holographic beam shaping and these beams we send them on the atoms, and they create repulsive potentials. We can lift the chemical potential on each individual lattice site. We can inhibit tunneling among certain like neighboring lattice sites. So we have a lot of control on a local scale here, not only probing but also controlling the state on a local level. The protocol that we typically use when we want to study non-equilibrium systems, and today I will focus on our non-equilibrium experiments, usually they look like as follows. So we start with a Mott insulating state where we have exactly one atom on each lattice site. We like Mott insulators for us because they're perfect initial state. They're unentangled. We know we have exactly one atom on each individual lattice site. And now we start from this and initialize our system. And today I will present you a one-dimensional experiment. So we have a one-dimensional chain of n atoms on n lattice sites, and this will now all the measurements are taken between 6 and 12 atoms at unity filling of the lattice. And then the next step would be that we quench on a certain Hamiltonian. So after this point, the system has been static, and we've just initialized the system. Now we start the evolution under a certain Hamiltonian. This could be the Bose-Hubbard model. This could also be another Hamiltonian. And then after a certain time t, we stop the evolution, and we take a picture of the quantum state. Now, in this case, you've seen that actually there are fewer atoms here than there. And the reason is that these fluorescence imaging techniques, they're parity projectors. So we can't really distinguish if there are 0 or 2 atoms or 4 atoms on a particular lattice site. So what we do is we do a little trick. We first expand the atoms along the orthogonal direction, and then we count the atoms in each column. And from that, we can have a full reconstruction of the many-body state. So we can really see the exact atom distribution on each lattice site. So what you have to think of is this is really kind of a Monte Carlo experiment. We just draw from all the distributions in Fock space. We just draw each time according to the probability, a snapshot of the quantum state. So much. This is really the procedure that we do for all the following experiments, and we will now look at 3 different regimes. The first one is just the Bose-Hubbard model, far from equilibrium. And afterwards, we will look at disordered systems, where we will study many-body localization and its entanglement properties. It was also already mentioned, for example, yesterday by Vedika. Quantum thermalization, the first question that we have to ask ourselves, actually, if you want to look at the entanglement in these systems, what does it actually mean for an itinerant system? That's something usually we think of spin systems. And then in these itinerant systems, we really have to make ourselves aware that already a single particle actually can create entanglement in the system. So if I just have a single particle that is distributed over 2 lattice sites, that's actually the same as a Bell state. So we're really looking at entanglement among different lattice sites rather than between different particles. That's more like just as a conceptual to remind you. That's the way to think about it. We're looking at entanglement among all these lattice sites that we have, and they can now host different numbers of particles. Now, if we want to measure the entanglement in a many-body system, actually there's a very nice protocol how you can do that that we've implemented in our lab. It's essentially a generalization of the Hongo-Mandel experiment, where you would send 2 photons on a beam splitter, and then if these 2 photons are identical, they would come out always on the same side of the beam splitter. Here we do something very similar, except that we generalize this to n-particle states. If I would have two n-particle bosonic states, and I send them on a beam splitter, which is identical to a swap operator, what I get is that afterwards I would always find even or odd particles on the right and on the left side if these 2 quantum states are identical. And so we can measure the particles on each lattice site. So if we would have our atoms and we prepare 2 identical quantum states, we couple them, and afterwards we would measure now the parity of the atoms within each part of the quantum system. What we measure by that is exactly the purity of the system. So we measure how identical are these many-body states, and that's a technique that we've implemented in the lab, where we can really measure the purity of globally of the quantum system, or also of subsystems. Now that we're looking at quantum thermalization, what we actually do is we start with the system. As mentioned before, it's a pure initial state. We start to evolve the system. We start a non-equilibrium evolution of the quantum system under unitary dynamics, which here is the Bose-Hubbard model. We have nearest neighbor tunneling of these bosons, and we have on-site interactions if there are multiple bosons on the same lattice site. And then after a particular point in time, we would now take a measurement. And what we expect is that the system would now locally behave as if it was a thermal state, but on a global scale, we still expect the system to maintain its purity because it's a unitary evolution. And that's exactly what we see. So if we measure now the purity with this protocol mentioned before, we see that as a function of time, we don't lose the purity. The state globally, this trace row squared here, really doesn't change at all over time. It's always the same, a pure quantum state. However, on the local scale, after some evolution time, we find that the atom number distribution on each lattice side actually resembles very much that of a thermal ensemble. So the overlap with a thermal ensemble is more than 99%. We have a really very thermal system. Although it's so small, already it resembles very much. Local observables already behave very thermally. Now we can also look at different subsystems. We can look at a single side, and we can look at, on the single side, the second order Renyi entropy, which is just the local purity essentially. So we look at this as a function of time. We find that there is this fast thermalization, then it stays constant. And for larger subsystem, it takes a bit longer until it thermalizes. And if we go for half the subsystem size, we already find a bit of evolution here, which means we are going away from this approximation to be perfectly thermal. And we can also look at other observables, such as the mutual information now as a function of the subsystem size, and we find here a very nice volume law for small subsystems. Now, I would now like to go on to the disordered system. So now we are going to study the phenomenon of many-body localization, which is a very similar protocol to before, except that now we would switch on disorder in the system during this evolution. So we slightly modify our Hamiltonian. And many-body localization has been already motivated very nicely by Medica yesterday. There are very different communities that are interested in it. For example, one reason is that since the particles are localized, despite of interactions, this draws attention in the condensed matter physics. We have a perfect insulator, or even more like a solid state environment. Also from the quantum information community, this is a very attractive system because it might serve as a memory, quantum memory, because the initial state stays intact for long times. We have a breakdown of the thermalization in the system, maybe the most fundamental of all the properties of many-body localization. But what I'm mostly interested here is the growth of non-local entanglement. So what we have here is a very subtle form of the entanglement dynamics that actually, very much in the spirit of the introduction of this talk, only reveals itself through non-local correlation observables, or actually entanglement entropy. Yeah, so these are very different communities. There's no quantum gravity here yet. Maybe they're actually, this will stimulate more interest in the quantum gravity community as well. This is the Hamiltonian. It's the very same as before with the Bose-Hubbard model, except that now we are adding a term with the disorder in the system. Now, it has actually been conjectured that you would actually see the entanglement entropy growing logarithmically in time after a very short initial rise. So what we find here is the von Neumann entropy as a function of time on the logarithmic scale. So we have an initial rise where these particles they spread, but they remain exponentially localized, so they spread just a little bit. Then they stay where they would be, and then without interactions in an Anderson localized system, we would expect a constant entanglement entropy, whereas for interactions, we expect this logarithmic growth in entanglement and entropy, a very slow growth, which comes from interactions between those localized orbitals, those exponentially localized particles. Now the question is now, when we have these exponentially localized particles, what does it actually mean for our system, where we always look in Fock space? We can't really see the exponential. And in order to understand what's going on here, we the first thing that we started to do was to look at the particle distribution. So, for example, when I would look at the left half and the right half, I could have one way to entangle these two subsystems by having particles that would cross the boundary. So I would have my global state in a very simple form would be in a superposition of still one atom on each lattice side, and then having particles crossing those boundaries, which leads to admixtures of more or less particles in the left subsystem. Now that's one form of entanglement which we call the number entanglement, but it doesn't capture the entire degree of freedom of the system. There's another way how the system can entangle, and that's what we call the configurational entanglement. And in this kind of entanglement, what we find here is that the particles have essentially they undergo correlated hoppings in the right and the left subsystems, such that after a while we have certain configurations of the particles in the left that always would go together with other configurations in the right. So we have one degree of freedom of the left subsystem, which is the atom number, and the second degree of freedom, which is the arrangement of those particles in the subsystem. And if we can if we can measure both of those degrees of freedom with our local probing of the state, we actually can capture the entire entanglement. So you can actually strictly show that this is exactly a sum of this number entropy and the configuration entropy. This works generically for systems that have a conserved quantity, because the density matrix essentially is block diagonal, and each block corresponds to one of the atom numbers, if the atom number is conserved, like for us. So this works very, very similarly for example, a spin system with conserved magnetization. And what's now exciting is that, since you can see this one here needs interactions. This particle needs to know about the other particle. You can also think of this as a virtual process where this particle would like to hop to its neighbor, but it doesn't. It first goes over here as a virtual process, sees the other particle, and then goes back. These are the kind of processes that lead to configuration entanglement. They need interaction, because I cannot have, with a single particle, I could not have configuration entanglement between the left and the right subsystem. Now this one doesn't necessarily need interaction. So this kind of entanglement is something that purely comes from spreading of particles in the system. So we have, in some sense, you could say we have entanglement between the subsystems, but not really between particles. If you have this kind of entanglement present. And it turns out that in this picture here, in this prediction here, we can actually find that in the Anderson localization system, we have this initial rise here, and then this constant value of the entanglement entropy. This is exactly the number entropy. So we have some spread of the particles until they remain exponentially localized, and afterwards there's no growth anymore, simply because there's no interaction that could enhance the entanglement in the system. However, if there are interactions present, the configuration entanglement grows very, very slowly in time, because particles are localized. So these virtual processes, they are very, very suppressed, but over long times they would accumulate entanglement in the system. So now the question remains, how can we probe this kind of entanglement? This time we don't prepare a second copy. This is what we were thinking if we can maybe do this in a simpler way. And what we did was, so the first thing is rather straightforward. We just count the atom number in one of the subsystems, and by that we calculate then the number distribution in the system, and from that we can directly calculate the number entropy. It's Pn log Pn. Since it's diagonal for the atom number. So this would be for a single site. We find a very, very non-thermal distribution here. So you find these bars here are the theory from exact diagonalization, and then these data points show you the data from a single lattice site, from a subsystem of a single lattice site, and we find that this distribution is strongly non-thermal. If we now compute the phenomenon entropy based on that, you find that as a function of disorder, there's a point at which we depart from the thermal prediction. So the thermal prediction here, as a theory, coincides very well with the experiment up to around disorder strength of around 5 times the tunneling. And afterwards, we very, very strongly depart from that. So we find that the system does not thermalize anymore, even if we wait very, very long times. So this is measured after 100 tunneling times, at which dynamics pretty much stops. Now we can also look at this for larger subsystems, for example, again, half the system size, and again, calculate now the number entropy. And what we find here as a function of time, again, we rise, but then after around 10 tunnelings times, we pretty much reach a steady state. So particles, they have this initial spread, but afterwards it doesn't change anymore. Very much in agreement, as you would also expect it for an Anderson insulator. But what about the second kind of entanglement? That's a bit more subtle to identify, in particular, if we don't measure exactly the Renyi entropy, but really just want to get it from snapshots of individual quantum states. So what we do is we look at not only one side now, but actually both sides, A and B, and we look at the configurations of those two. And then we take many, many snapshots and compute the probabilities for the configuration A and configuration B to occur together with their individual probabilities. And if we find the deviation of these two, we know that there are some correlations between those two arrangements, which means that the left and the right subsystem must be entangled. So if we sum now over all the configurations that we could have in subsystem A and subsystem B, we can construct a correlator here, and it turns out the correlator here is exactly proportional to this entanglement entropy. One way to think about this is that the phase degree of freedom here is kind of homogeneously distributed. There's no additional information in the phase degree of freedom that would go beyond that. So we can just rescale that. So essentially it's a transformation into a slightly different basis. So we measure now although we just measure in one basis, we capture the entanglement of the system. So in time, this actually since this correlator here is exactly proportional to the configuration entanglement, we can also use this quantity to make claims about the scaling as a function of subsystem or as a function of time. Now, if we look at this now as a function of time here, this is now on a logarithmic scale, the time from around the 10th of a tunneling time to 100 tunneling times, and we find a very nice logarithmic, consistent with the logarithmic growth of this entanglement. So now adding these two entanglements together, the number entanglement and the configuration entanglement, we can find this predicted behavior of the entanglement entropy, of the entire entanglement entropy in the system. And we find really that we don't have an Anderson system here, but we really have this slow growth over long times that stems from interactions in the system. Now, in the last part of the talk, I would now like to focus on the critical dynamics of the system, because the regime for intermediate disorder between low disorder and very strong disorder actually has a lot of analogies with quantum phase transitions as we know them from ground state or equilibrium systems. So usually when we think about critical dynamics at a quantum phase transition, here again, just as Ignacio also mentioned before, this would be the phase transition from a superfluid in a Mott insulator as probed in cold atoms, where we have here in an interference pattern we find some global phase, whereas this is destroyed in the presence of strong interactions. The same is true for generic interactions. We would usually probe them by looking at different positions as a function of some tuning parameter, and now looking at the, for example, correlation length, or would also look at maybe the elementary excitations and find divergences. Now, the situation looks much different for a many-body localized system, because now, in general for non-equilibrium systems, because now we're having a state that is a superposition of many different eigenstates. So our critical behavior is no longer determined only by this ground state here, but by all the other states. So and you see here actually depicted the entanglement of each individual eigenstate. Now, if I sit in a superposition of all those different eigenstates, the situation becomes very complex. So all we can do is we can now look at these kind of systems on a macroscopic and on a microscopic level and hope that we can bring those together to further our understanding of this kind of critical behavior. So first I would like to show you what we do on a macroscopic level, and one one thing that we looked at were the transport properties at a critical point. Actually, we can from density correlations we can extract how far particles like to spread in the system. So if a particle, for example, would hop from one lattice side to the other, I would find the double and whole pair. So that means that if I look at the typical distribution where I find the particle, so where I find an empty side and a doubly occupied side, I also find how far typically particles want to spread. So that tells me something about the transport in the system as a function of time or disorder strength from the density correlations. So what we do is we take our snapshots, and now we define the average distance that particles would hop and look at this as a function of time. And now first, in the presence of weak disorder, and on the thermal side of the phase transition, we find that just within a few tunneling times, we are reaching the system size particles perfectly spread across the entire system. So this is on a log scale where time and where both time and this transport distance here are on a logarithmic axis plotted. And if we now look at this spatially, so after very long times, after 100 tunneling times, if we look at the density correlations as a function of distance, we find a rather homogeneous distribution, which really means that particles like to spread across the entire system. All lattice sites are equally coupled, there's hopping among all pairs of lattice sites with an equal strength. Now, in the many-body localized system, we find a very different behavior. So really, within few tunneling times, we have a rise, but then afterwards, the transport distance remains almost constant. So there's an initial spread of the particles, but afterwards there's a localization. And we can find this even better when we look again as a function of subsystem size, where only nearest neighbors are strongly coupled, but all the other lattice sites are uncoupled. So particles really only would like to go to their nearest neighbor, but no further. Now the situation becomes strikingly different in the critical regime. What we see here is that we have a very slow growth of this transport distance, and this is supported by a network. So you find here there's kind of at some distances lattice sites are strongly coupled, and at other distances they're not so strongly coupled. For example, at a distance of 4 lattice sites, I have a lot of tunneling. So if I'm here and I would hop 4 lattice sites further, there's a lot of coupling there, but there's almost nothing, for example, for a distance of 2 or 3 or even 8. So there are some distances that are favored where the density correlations are stronger than others. Now, the understanding the structure of this is very non-trivial. You can see that it coincides very well with our exact organization calculation. So we can predict the behavior of the system, but understanding what exactly is going on is not so easy. One question that we asked ourselves is, where we can quantify this by fitting power laws to that, and from that extracting the subdiffusive behavior, and really find that as a function of the disorder strength, the system becomes more and more subdiffusive until eventually the transport fully stops in the system when we are in many-body localized systems. Now, this complex network. The question that we asked ourselves is, how complex is this network? Does it, and what role plays the entanglement in the system? And in order to understand this better, we were looking at higher order correlations. In this case, the connected higher order correlations, where we subtract all the trivial contributions from lower orders. So we're looking here at 2, 3, 4, and more lattice sites. How strongly are the correlations among those lattice sites to identify how non-separable is this subgroup in the system. So these can now be consecutive or non-consecutive groups within the system. And what we find is that in the thermal regime, so what you find here is what you see here is the correlation order. So that we go up to 8th order, where we look at the higher order correlations, and we do this now as a function of the disorder, from weak disorder to very strong disorder. So we're crossing the thermal, the critical, and the many-body localized regime here. And you find that you see that in the thermal regime, we have a decay as a function of the correlation order. So we have strong 2-point correlations, but afterwards it gets weaker and weaker. So the system is not very strongly correlated at higher orders. Very similarly also for the many-body localized system. So we have some 2-point correlations, but afterwards the system becomes less and less ordered. And it's very, very different in the critical regime, where the correlations don't really decay. So we have a strongly correlated system in its sense, very, very strongly correlated system. No matter how high I would look at the connected correlation functions, I always find very, very strong correlations in the system. So this, although we might not really be able to explain exactly what's going on, this connects very nicely the microscopic and the macroscopic picture, where we have these strong correlations that kind of, since they build up, they slow down the transport more and more, and make the system really a very complex system that is very hard to simulate on classical computers. This leads me maybe to, as a cartoon picture at the end. I would like to leave you with these three depictions of our system. In the thermal regime, we have global entanglement structure. All particles are equally, or all lattice sites are equally coupled. In the many-body localized system, we have only nearest neighbor correlations, with a bit of a shading here for this hidden pattern, where particles actually have some non-local correlations, but they're very weak. And then in the critical regime, we have this kind of fractal behavior, where some groups are correlated at 2-point, 3-point, 4-point correlations, but we really have all kind of correlations across the system, which makes it so complicated to describe it. So what we are looking at right now is to maybe further our understanding of entanglement in the system. One route that we are pursuing right now is to understand from machine learning what exactly happens here. So we could think, okay, if I can construct a correlator that can capture the many-body localized entanglement growth, maybe you can also train a network to do that. And indeed, it's actually possible to if you inject multiple snapshots into a neural network, it is able to distinguish thermal Anderson many-body localized states and capture very well this logarithmic growth of entanglement. And another thing that we are working on is to actually increase the system size. So here are some preliminary shots of 24 sites at unity filling, 24 bosons on 24 lattice sites. That's a very, very large Hilbert space where the many-body localization calculations, which they can't access anymore. So with that, I would like to thank our team, in particular Marcus, our PI, and our theory support from Vedika and Suman Choi, and thank you for your attention.